I can, yes. Thank you very, very much. Sorry, I was distracted by handing out documents, so I'm less prepared. Okay, we have transfer function, we have TF. What are some other things we learned? ODE 45, which does what? And spits out? No, it does not spit out the transfer function. This one takes the integral and it solves the differential equation. So it takes an integral numerically. Okay, so in other words, solves the ordinary differential equation. And there's one last one that was probably on the really important list. What was the last really important one? State space, yeah, thank you. So SS stands for state space, and this is how we create a transfer function object by providing the state space matrices. Okay, so if state space is written as, and this was important on your quiz, x dot equals ax plus bu, and y equals cx plus du, then what SS wants is A, B, C, D. A, B, C, D. Okay, and we're going to practice that one today at the very end of class. All right, that's all I'm going to review from last week. So right before we did our MATLAB workshop, we started working on state space form. We're going to finish up state space form today, okay? So we're going to do that by doing just two examples, one that's a little bit on the easier side and one that's a little bit more complex, but we'll get through it. And then at the very end, we're going to use MATLAB to model that final state space system of equations. All right? Okay, so let's hop in. So day 5, state space representation part 2. Like I said, we're just going to do two examples. That's all I have for you today, are two examples. All right, and both of those examples, I'm going to give you a system, and we need to write that system in its state space form. Okay, so let's, again, remind me, what did I just write above? What is state space form? X vector dot, yep, equals AX plus BU. Okay, is that it? Very good. CX plus DU. I'm going to try to drill that into your head because a lot of people miss this on the quiz. And this, if you learn anything that sticks in your head maybe 5 years out of this class, I want you to be able to tell me that state space form is x dot equals AX plus BU and y equals CX plus DU. That form should be like always there. You think of Dr. Higgins, you think state space form. I hope not, actually. All right, what is this first equation called? We usually put a name to it. Any ideas? This one is the state vector. This is the state equation. We were getting there. I knew you had it, Omari. And then the last one is what? What do we call this vector? The output. So we call this one the output equation. See, this is why I have to write on an iPad because I can never figure out how much space I need. There we go. All right, so this is what we want to massage our system into. We want to be able to write it in this linear algebra form. What is the very first step that I need to do? Right, my equations of motion, absolutely. So find my equation of motion. And how do we do that?
Free body diagram?
Yeah, we can do a free body diagram, absolutely. So let's work through that. Is what's above, is that a free body diagram? No, it's just a picture of a system. If I'm going to draw a free body diagram, I need to choose the inertia that I'm drawing the free body diagram for. And there's only one thing that has mass in this system, so we're just going to draw M. And then I need to draw not the objects that are connected to it, but the forces that are connected to it. So F here is absolutely a force, so we can just transcribe that one. That's our input force. This is what we as the control engineers get to decide is the input. And then what are the other bits?
You got gravity.
I'm actually going to pretend that this is in the plane. I'm looking down on top of it. Not going to worry about gravity. The spring force. Now that spring force, should I draw it to the left or to the right? To the left. Okay, can you explain that logic, Alex?
The spring wants to return back to its natural state, so it's going to be pulling it. If the S of T is going right, then the spring force has to go straight.
Yes. So it's safe for us to assume that the way that I've drawn it is when the spring is at its natural length. So safe to assume it's at its natural length. So if we pull it to the right in the direction of positive displacement, positive S, that spring is going to want to pull it back. Okay, so it needs to have a force going back to its original position. And what is that force equal to? Ks, right? Because it's equal to the displacement. Yep.
For output, why does it say X of T?
Because it's a mistake. Thank you. I originally wrote this problem with S, and then that became an issue with state space form because there's all these X's for state space, and I wanted to refer to displacement as something other than X. So absolutely our output should be the position or displacement S. All right, one last one. What's our last one? The damper. And the damper always opposes motion. No matter which direction you're going, a damper always opposes motion. So if we assume a positive displacement in the direction of positive S, the damper will always go in the opposite direction of the motion. And it is equal to C times what? S dot, yes. So a viscous damper, the force is proportional to the velocity. Okay, now I can go back to dynamics, Dr. Higgins' favorite class. Sum of forces equals mass times acceleration. Now let's sum our forces. What should my forces be? Beautiful. Excellent. Okay, for the rest of this problem, we're going to want S double dot to be completely on its own. So I'm going to go ahead and divide by M here. So we should have F of T over M minus K over M S minus C over M S dot equals S double dot. Beautiful. Okay, so that's our equation of motion. All right, what's my next step? No, I'm going to leave it just as it is here. This is going to be just fine with just the S double dot on the one side.
You're counting you gotta count the state variables?
Yes.
Figure out your state vectors?
Yes. So one, I need to figure out how big is the state vector, how many variables do I need in that state vector, and then I need to figure out what are the variables in that state vector. So number two, I'm going to say how big is the state vector. And remember that state vector is this guy. It's just the x vector. That's my state vector. So we need to figure out how big is it. We know that it's a vector, so it has one column, but I don't know how many rows. So what is the procedure for figuring out how many states we need? We know there's some subtracting, there's potentially some adding.
You have to figure out the highest and lowest order for all variables.
Very good. Okay, so I'm going to look at, let's look at S here. So we decided that F is our input, so I'm not going to worry about F. In other problems, we didn't necessarily differentiate what was the input and what was the output. We said find all of the highest and lowest order for all time-varying variables. But for this, when I'm putting it in state space form, I'm going to treat the input as a completely separate vector. Okay, so that is, in fact, I could even go ahead and write U as a vector is really just the scalar f of t. So I'm not going to worry about that one. I'm only going to worry about this time-varying position S. All right, so what is my highest order of S?
So 2.
Yep, we have an S double dot here, so that's 2. And what is the lowest one represented?
1, 0.
So this one would be 1 because I have one derivative of S, but there's a lower one.
0.
0, right, because I have an S here that doesn't even have a derivative on it. So that order is 0. Okay, and so I know that n is equal to the subtraction of the highest order minus the lowest order. So 2 minus 0 equals 2. So my state vector here is n by 1. And we said n is equal to 2. So x is, you might even see it written like this, or 2 by 1, which basically just said that the x vector is in the space of all real numbers that have 2 variables, 2 rows and 1 column. So we're just saying that each of the components of x is a real number. All right, so now we need to figure out what actually goes in there. What are the contents of the state vector? I know it has 2 positions. There's something here and there's something here, but what are they? Okay, so what is the procedure that always gets us the correct answer?
Start with the lowest one and then work your way up.
And then what about the last one? Should we include the highest order?
No.
No, we don't include the highest order. So lowest order of S here is simply S, that's the 0th order. Then we go up in order, which would be S dot. My highest order is S double dot, and that's the next one. And I do not include the highest order. So I do not write S double dot, which is good because I didn't have space for it anyway. Easy peasy. X is S, S dot. All right. We actually went ahead and skipped a step. I would say the next step is what is your control vector? Or in other words, your input vector. And the most general form is for U to be a vector. But we know for this particular problem, U is just a scalar, which is the amplitude of that force F of t. What's your output vector? If I scroll back up to our picture. What was that?
Output equation?
The output equation, yeah. So it could be a vector, but we're just doing a single input, single output system. So the output is just the value S of t. So y could be a vector, but for this particular problem, it's just the scalar S of t. Very good. We're getting there. We're almost ready to put it all together. What's the next thing that I need to figure out? Not quite yet. We need one more thing before we start with A. What's the far left side of the state equation? Is it X?
X dot.
X dot. Beautiful. So I need to take a time derivative of my state vector. So what is X dot? That's just d dt of X, where I just add an extra dot. Okay,
Oh, never mind, I can't see.
sorry.
Very good.
Here?
I have a question about for steps 4 and 5. You're
Yes,
not
sir.
including the vector notation because they're just scalars here?
They are just scalars here, yep. You could still say technically it's a vector, but it's a 1-by-1 vector. Yep. Okie dokie. All right, now we need to do some manipulation. We know that x dot equals ax plus bu and y equals cx plus du. So I'm going to say manipulate. Let's fill in what we know. I already just found x dot, so let's go ahead and put that on the left-hand side. I know that the left-hand side is s double dot, at least for my first equation. I know that A is a matrix, and in fact, I know that A is a what type of matrix? It has to be square. In fact, you can tell me one more thing. It is n by n. Thanks, Nadal. Yes, so A is n by n, which we found out previously is what? What is n for this problem?
2.
N is 2, which means our state vector has 2 items, so A must be 2 by 2. So there's something that goes here, 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 and here. And then I've got my state vector, which is just s dot. That's x, plus something times u. And we decided what u was back in number 4. What was that? F of t. Good. All right. So we need to figure out what the heck is b. What is the size of b? So we need to go back to some of our linear algebra properties. Okay. So let's use this first term as an example. This first term multiplies a 2 by 2 times a 2 row by 1 column. And how do I know what the output of this multiplication will be, Jerry?
The 2 outer terms?
The 2 outer terms. 100%. So that will result in a 2 by 1, which is incredibly important because it has to be equal to a 2 by 1 because that's what I have on the left-hand side. 2 rows, 1 column. Okay? So that means this second term also needs to result in a 2 by 1. And I'm multiplying whatever the heck b is times a 1 by 1. So what do we know about b?
2 by 1.
It needs to be a 2 by 1. Okay, so based on what Jerry says, we know that the number of rows has to be 2 because it has to result in a 2 by 1. But how did you know that it was a 1 column at all?
The last 2 have to match.
The inner dimensions must agree. Okay, so this has to be equal to this. So we absolutely know that this is a 2 row, and that's way too far away. 2 row by 1 column matrix B, and this is U. All right, very good. So even if you don't remember all of the sizes of all these things, it is pretty much sufficient to know that A has to be square, it has to be n by n, and to know the size of your input vector, you can always back out what B is. You don't have to memorize it. All right, I'm going to erase some of these arrow notes. All right. Let me add an additional line to maybe try to make this a little bit easier. I'm going to pull my equations of motion down so that we can play with them a little bit more. In fact, I'm just going to pull this one. Copy. Paste. Okay, so we have one equation of motion. What can you tell me about this top row equation? What can you tell me about this top row equation? We want to write what's on the left in terms of our state. What is on the left-hand side in that top row equation? S dot. Okay. Is S dot a state? Is it contained within my x vector?
Yes.
Yes.
I sure hope it is. Unless I'm crazy, that's an S dot. Very good. So all I need to do in this top row is to pick out that S dot from my state vector. So if I want this top row to read S dot equals to S dot, how many S's do I need to pick out?
0,
0. How many S dots do I need to pick out?
1.
1. Okay? When I multiply this top row and I dot it with this column, I'll get 0S plus 1S dot equals S dot. That's it. That's all I need to do. S dot equals S dot. Josh?
Can you repeat that?
Yep. Absolutely. So when we do our matrix multiplication, let's maybe review matrix multiplication a little bit. So 4, 2, 1, 8, maybe 1, 2. When I do matrix multiplication, the first thing that I do is I need to take this top row and dot it with this first column. So the result here on the top should be 4 times 1 plus 2 times 2. So I should get 8. Did I mental math right? Usually I suck at that. So this top value is 8. Okay, and then this second row, matrix multiplication, is this second row of this column dotted with, again, the first column of the second term. So I should get 1 times 1 plus 8 times 2, which should be 17. So the result here is 8, 17. So just a quick review on matrix multiplication. So when I do my matrix multiplication for just this top row of 0, 1, S dot, what is the result? I get 0 times S plus 1 times S dot. So this first term goes away, and I just get S dot. Does that match the vector on the left-hand side in just that top part? Yeah. So that means we did it right. That's what we want. We want to make the right-hand side equal to the left-hand side. Okay. Did we need any F inputs in that vector? No. So what should I do in this last highlighted bit? 0. Very good. All right. The bottom one is a little bit more complicated. The bottom one is where we bring in that equation of motion. So I'm going to rewrite this. I'm just going to flip it around. So I want the left-hand side over here to be S double dot. So I need the force to force the right-hand side to be something times S plus something times S dot plus something times F of t. All right, so I'm actually going to rearrange these terms so it makes that nice and easy. So I'm going to say this is minus K over M something times S minus C over M, which is something times S dot, plus F over M, which is something times F of t. Okay, so what goes in this first component here?
Negative KM.
Beautiful. Minus K over M. What goes in this second slot? Yep. Minus C over M. And what multiplies F of t?
1 over M.
1 over M. I'm going to keep that. I highly recommend, if you want to double check that we have done this correctly, go ahead and compute the matrix multiplication. It should end up being that S dot equals S dot, and the second row should be S double dot equals everything in the equation of motion. Yep, Jerry.
So I was wondering why for the first row on the S dot, we don't bring in our equation of motion. Why do we only do that for the second one? Like, would we always have a situation where it ends up being 0 or 1, or what would be a situation where it would just be 0 or 1 there?
That's a great question. When would it not be that? For
I'm wondering, is it multiple equations of motion where we would have something other than 0 or 1 there?
So we are going to do multiple equations of motion on the next problem. we do still have a row that's 0, 1. It becomes a 4x4 matrix, and we end up with 2 rows that have a 0 and a 1, and 2 rows that are not 0, 1. So that will still happen even if you have multiple input, multiple output. That's a great question, and I don't entirely know the answer off the top of my head, but I can imagine an example in which the orders involved in the equations of motion potentially result in you not having a line that's 0, 1, but I need to get back to you. Yep. Sorry, I don't have a great answer there.
No worries.
Yes.
Is there something like that on like homework? Because I know when I was looking at the homework, to do basic homework, there was like a big there's like a big matrix, so, and you said like, it's gonna be like all in the same pattern, right?
Mm-hmm.
Okay.
It'll be very similar.
Okay.
Yep. So the procedures that are numbered, you can do those same procedures for any problem, and they should help you figure it out. And we're gonna do it for a more complex problem in just a second. Are we done? Did I find that?
No.
Nope. I only did the top part.
C and D.
We need to figure out this other equation, y equals cx plus du. So again, I'm going to start out by writing everything that I absolutely already know to be true. So for one, I know what y is. I know that y is just s of t. So this is my y vector. Then I have something multiplied by x, and I know what x is. That's ss dot. And then I know what u is. U is, what did I find out is u? Just f of t. So again, I'm going to use my matrix multiplication here to figure out what are the size of C and D. So the left-hand side, what size is the left-hand side matrix?
N by N.
Specifically for this one.
Oh, 1 by 1.
This is just a 1 by 1, it's a scalar, but we can consider it as a 1 by 1 matrix. Okay, so that means each of the terms on the right-hand side need to result in a 1 by 1. Okay, so this one is 2 row by 1. If I want the outer components to be 1 by 1, that means this has to have 1 row. The inner components have to agree, so this needs to be a 1 by 2. 1 row, 2 column, something here, something here. And then D, this is already a 1 by 1. If I want the outer dimensions to be 1 by 1, this has to be 1. Inner dimensions have to agree, this has to be 1. So D must also be a 1 by 1. So just one item in there. Right? So as long as you know X and you know U, you can back out what C and D are, at least the size of them. Okay, so I want this on the left-hand side, S of T. I want the result of everything on the right-hand side to give me S of T. Is S of T a state?
Yes.
Yes. So again, this one should be fairly simple. I just need to multiply this S by 1 and this S dot by 0. So I do that by setting 0, 1. No, other way, sorry. Yep. 1, 0. 1 times S, 0 times S dot. What about D? What should D be?
0.
Yeah, do I have any F of T contained in S of T? No, the way the C times X takes care of it. I have S of T equals S of T, so this is just 0. Okay, that's it. I'm going to highlight our final answers here. So this was our, oh God, that's bright. That's a little exuberant for me. That is our state equation, and this is our output equation. Ta-da! Okay. Questions? Before we go on to Big Bertha here. Yes.
On output, why did you put 0 by the F of t?
Because f of t doesn't show up in s of t. When I multiply c times the state vector x, I get s of t.
Okay.
That's everything. I just want s of t equal s of t.
Alright.
Yep. So we reviewed this, I believe, last week. This is called your feed forward matrix. It allows us to say that sometimes our input has a direct result on the output. And that's not the case in this problem. In this problem, our input has to go through the dynamics of the system in order to result in an output. But it is possible that, like for instance, if our output was not a position, but it was like a force, we say if we add a force, that comes straight out in the output. So it's a feed forward. It just shows up. So if that were the case, it's that D term that would allow it to mathematically happen. All right, let's do this next one. Oh, I wish I'd erased that. I wish that I had erased what are the inputs and outputs. What are my inputs?
I don't know, F1, F2.
Oh, wow. You're so smart, Hannah.
I have my moments.
Yeah, I have an input force F1 applied directly to this first mass, and I have an input F2 applied directly to the second mass. Okay. If I were to add only force 1, would it only affect the position of M1, or would it also somehow affect the position of M2? Yeah, we call that being coupled. So even though I'm applying the force only to M1, it does cause some effect in M2. So we call that coupled. They are coupled by the fact that they are mechanically connected by that spring K2. Same thing happens to F2. If I pull F2 to the right, I'm going to result in some motion of M1 and M2, not just M2. Okay, what are my outputs?
Crazy. S1, S2.
Oh, you're so wild. S1 of T, S2 of T. Wild and crazy. Yes, that is absolutely correct. All right. Let's see. Let's find those state space equations. Remind me, what is the state space form? I want someone on the left-hand side over here to tell me. Y'all are shy. Don't be shy. Don't make me call on you either. You know whose name I'm going to call? John, what's my state space equation?
Oh, what, the x dot equals ax? No, that's not.
Yes, I'm writing it.
Yeah, ax plus bu.
Overthinking.
Is that it?
Oh, you need the y also?
Yeah.
Or y equals cx plus du.
Beautiful. Again, this, if you remember anything, 5 years down the road, I want it to be this. Your state space form. Okay, so we need to somehow get this system written in terms of these two equations. So what is my first step? If you go back to your previous problem, what is the first step I did last time?
Equation of motion.
Find equations of motion using my free body diagrams. I'm going to give you all, I can't write and speak at the same time. I'm going to give you 2 to 5 minutes, depending on how I feel, to find those equations of motion yourself. Go for it. How many bodies are in this problem?
2.
So how many equations or how many free body diagrams would you draw?
2.
2. And you should end up with an equation of motion for each. Do it. No, do it on your paper. You're not gonna learn through osmosis.
Working pretty well.
Straight lines are hard.
Go back to the picture.
Back to the picture. You're welcome. Mm. Question, Jerry.
If you're pulling on, for mass two, if you're pulling in the F2, or I guess positive S2 direction, wouldn't K2 want to pull it back towards negative A2 position?
This is the trickiest term in this whole thing. There are a couple of ways to think about it. The easier one to figure out is how moving in the S1 direction for M1 will cause the K2 spring to react, right? If I only move S1 to the right, then it means I'm compressing that spring, and it's gonna push back against me. So one way to think about it is that what happens between M1 and M2 needs to be equal and opposite.
Okay.
So if it pushes to the left on M1, it has to push to the right on M2.
Okay.
Another way to think about it is to try to figure out how that spring reacts only if you move S2. So if you move S2, the way that spring pulls or doesn't pull depends also on how much S1 has moved, because it is so coupled. So if you move to the right, it would push on me on M2 if S1 minus S2 is a positive number, I think. Is that right?
That makes
This
sense,
was
yeah.
positive, gonna be compressive.
Yes. So if S1 is greater than S2, then the spring will push on me as M2. So it goes S1 first minus S2. Alex?
So just so long as you have them equal and opposite, it wouldn't really matter if you flip the two signs. Like if you flip the arrow for M1 to go the other way, then you flip the arrow on M2 to go the other way. So
Especially those are-
You would have to switch the order of the terms within the parentheses as well.
That's what I changed to.
Yes.
I thought as long as you're consistent, I thought as long as they're opposite arrows, you'd be fine. The math would end up,
but your negative will switch it. So the only way that it stays consistent is if you switch the direction and multiply by -1.
Okay, that's what I had, yes, that's what I was wondering.
So if this really confuses you, you can see it done the other way in Dr. Hubicki's lecture video, because he does it the other way. I like to think of it first as it's very easy to tell what happens if I move only S1. If I move only S1, that's easy to tell.
That makes sense.
And then it's equal and opposite. Okay, I will say that is a tricky part of this problem. Okay, so now I have my equations of motion. I have something about S1 double dot, something about S2 double dot. Again, I'm going to rearrange so that I have S1 double dot all on its lonesome on the left. S1 double dot, so I'm going to divide by M. And in fact, I'm going to try to group these the way that I did before. So I'm going to put, let's go ahead and distribute my S's. And I want to give all of my S1 terms, then all of my S2 terms. So let's see what that looks like. That would be something like minus K2 S1 over M. Minus D1 S1 dot over M.
Should we use C's?
Whoops, I missed. You can, but the way that I drew the picture is I labeled it D1. It doesn't really matter. And in fact, a lot of people like to use B's instead, so it doesn't matter. It's a coefficient. I forgot a term here. So this needs to be minus K1 S1 over M plus K2 S2 over M.
Should we be putting like the subscripts on the M's though, like?
Yep,
Find it's M1.
Yep. M1, 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 M1. I did it right on the right-hand side. Thanks, Angela. Where was I? I need an S2, so plus K2 S2 over M. Plus F1 over,
Did you write that
M1.
twice?
where did I, yeah.
K2, S2.
Yeah, sorry.
D terms though. Instead there. No, that one's fine.
I should,
You did them out of order, why'd you do that?
because it's going to be helpful later. So I got both my S1 terms and S1 dot. Now I need my S2, which is plus K2 S2 over M1. And then I need to not forget F1 over M. Is that okay? Sorry. Tried to answer in the middle. Not a good idea. Okay, S2 double dot equals minus K2 S1 over M2 plus K2 S2 over M2 plus F2 over M2. All right, what's my second?
Professor, I don't know if you were explaining this earlier, but wouldn't K2 for M2, wouldn't that be positive because you put them both going to the right, both the force and the spring force?
Yes.
Okay,
This one?
yes.
Yes, ma'am.
So then,
Yep.
okay.
I need to follow through. All right, good there? All right, what's the next thing I need to do?
Find how many, what n is?
Yeah, yep. Figure out how big my state vector is. And to do that, I need to figure out my highest and lowest order of my inputs. Okay, what's my highest order of S1?
2,
What's my lowest order of S1?
0,
What's my highest order of S2? Lowest? Good job. So n is equal to what?
4,
Very good. Which means that A is
4 by 4.
4 by 4. Very good. What's my next question?
What actually are they?
Yep, what are the contents of my state vector x? I know now that x has 4 slots. 1, 2, 3, 4. What do we think they are?
S1, S2, S1 dot, S2 dot. I don't know how we're wording that, but if
Yes, the order that we normally put them is to start with one variable and work up to the next second highest order and then move to the other variable. So I have S1, S1 dot, S2, S2 dot. It is absolutely theoretically okay to change the order of these things, but you will get a different A, B, C, and D matrix. But this is the canonical way, if you want to call it that. All right. So notice here, someone has asked in the past, how can I have S2 dot in my state vector if it doesn't actually show up in either of my equations of motion? Is that okay? Or is that not okay?
what's the question?
So S2 dot is a member of my state vector, but it doesn't show up in either of my equations of motion. Do either of those equations have an S2 dot in them? No. Is that okay or not okay? It's fine. Totally fine. All right, what's my next step?
Take an A.
No, you always like to skip the next step.
What? We're finding these?
Okay, we could find you. I actually have that as a later step, but we need to find what is x dot. Find x dot. X dot is just the time derivative of x, so I just go through and add an extra dot. I'm just going to scroll back to see if I'm being at all consistent. Nope.
Step 6 was the.
Yeah. So we need to also know what is the control and the output vector. I'm just going to lump these all together. What is our input vector? U.
F1, F2.
Beautiful. You told me that at the very start. What is my y vector?
S1, S2.
Yep, those are the two things I care about. The position of mass 1 and the position of mass 2. All right, I believe next all we need to do is manipulate our equations. Okay, tell me that state form again. Gonna beat it into your head if I have to. Someone on the left. Why are you so shy?
I'll move them to the left side.
Yeah, Josh.
X dot
Yep.
equals AX plus BU,
Beautiful, thank you. What's the next one? There's another one.
Y
Mm-hmm.
equals CX plus DU.
Yay! Thanks, Josh. Beautiful. This is what we need to get our equations into the form of. All right, I'm going to go grab our equations of motion again because we're going to need to refer to them. Copy. Paste. Okay, I'm gonna help you set up most of this, and then I'm gonna have you fill in what are the values within the matrices. So let's fill in x dot. We said x dot was S1 dot, S1 double dot, S2 dot, S2 double dot. That's this thing here. Equals a 4x4 matrix A times our state vector U. S1 dot, S2 dot, plus something times our input vector U, which we said was F1, F2. All right, so we know A is 4x4. This is a 4 by 4, 4 by 1. So that should give us a 4 by 1.
Dr. Higgins, I
Yep,
think you repeated the S2 dot in the 4x1.
yep. Got dot happy. Thank you. So what is our B matrix? What size is B?
4x2.
4 by 2. Thank you. Brilliant. So 4 rows by 2 columns. All right, take 5 minutes, try to fill in what these matrices are. We'll come back together and do y. Unless you're super speedy, you can go ahead and start on the y equation.
Why does the top right and not have a subscript?
Because I goofed. Thank you so much. M1.
I think also previously you.
Did I? Way back up here? Yep. Thank you. Okay. Is S1 dot a state?
Yes.
So I just need to use this first row of A to pick out which state that I want. So is it this first state S1?
No.
Nope, so a 0. Is it this second state S1 dot?
Yes.
Yes, so I put a 1. Is it S2?
No.
S2 dot?
No.
0. Okay. I can even go ahead and skip down 2 rows. I could go ahead and do S2 dot the same way because S2 dot is also a state. So this could be 0, 0, 0, 1. All right. So Jerry, do you see, oh, I think Jerry disappeared. Oh, you moved. So that pattern still shows up. All right. Okay, S1 double dot, we need to use our equation of motion. And these two terms both multiply S1. So I'm actually going to pull these into one term, K2 minus K1 over M1, all times S1. So might have to write a little bit tiny here. Minus K1 minus K2 over M1. Okay, what multiplies S1 dot?
D1 over M1.
Good. Minus D1 over M1. What multiplies S2? Positive K2 over M1. Well, what multiplies by S2 dot? What goes here? 0. Very good. And then do I have an F1 in the top row? So there was 0 for S1 dot. For this second row, I have, 0, 0 here for that top row. And then for this second row, I have just an F1 times 1 over M. M1, and nothing, no F2 shows up. All right, is there either an F1 or an F2 in our S2 dot equation? Nope. So that's row 3 of B. And then S2 double dot, I need our second equation of motion. What multiplies S1? What multiplies S2? Oh, sorry. What multiplies S1 dot? 0. Very good, Alex. You read my mind and not my mouth. What multiplies S2? What multiplies S2 dot? 0. And what do we multiply times this U vector? 0, 1 over M2. Good job. Excellent. Ooh, that was a doozy. 4x4s get pretty large. That, my friends, is our state equation. AX plus BU. Are we done? We got to do the Y vector. Yep. Y. Let me go ahead and add this just for reference. Y equals CX plus DU. I know my Y vector is what? S1, S2. I know my X vector is what? Great. I know my U is F2. Good. All right. I can use my linear algebra to figure out what size these are. This over here on the left is what by what? 2 by 1. So everything on the right-hand side needs to result in a 2 by 1. So this is a 4 by 1, and I need to multiply it by a 2 by what? 4. 2 rows, 4 columns. 1, 2, 3, 4. 1, 2, 3, 4. All right, this is a 2 by 1. I need to multiply it by a 2 by 2. Good. All right, is S1 a state? Yes, so I just need to pick it out of my state vector. So 1, 0, 0, 0. Is there an F1 in it? Is there an F2 in it? Nope. S2, is that a state? Yep. So 0, 0, 1, 0. Is there an F1 in it? Is there an F2 in it? No. All right. You did it. All right, I have just enough time now, if MATLAB cooperates, to simulate this system on MATLAB.
Dr. Higgins, would we ever be given the output, like equations to where it would look different than kind of this form? 'Cause it seems like this was similar to the last problem where it was all just ones and zeros.
Yes, yes. So let's say, hold up guys, I'm answering a question, try to be quiet. The output equation here assumes that we have access to measure both S1 and S2, meaning we have some sort of sensor that can tell us what is S1 and S2. It is highly possible that we either don't have enough money or we don't have the right sensors to measure both S1 and S2, in which case we will have a slightly deprecated output equation in which we cannot observe all of the states that we want to observe, and it'll look slightly different.
Okay.
Yep.
Well, that's when I store in terms of small sensor values.
Yes,
If
it's
S1,
possible.
S2, it was like, I don't know, the temperature or something, but you only have, maybe temperature's not a good example, but some kind of other, like the volume of it, and you had three, like, I don't know, dimensions.
It's possible.
Right down to myself.
All right. I'm not quite done. I've got 5 more minutes. Okay, we're going to simulate a state space system. I'm going to start out with clear, CLC, close all. I'm going to need to define a bunch of parameters. I need M1, M2, I need, let's see.
D, K1, K2.
Yep,
Yeah, that's it.
there we go. Let's use,
And that's
I'm gonna say M1 equals 2, M2 equals 1. I'm gonna assume these are all kilograms. We're gonna use metric units. K1 is 10, K2 is 20, D1 equals 1. So our A matrix, 0, 1, 0, 0, that's my first row. Second row, minus K2, minus K1, all over M1. Second column, minus D1 over M1. Third column, K2 over M1. Fourth column, 0. Next row, 0, 0, 0, 1. Next row, K2 over M2, 0, minus K2 over M2, 0. Did I do that right?
Yeah.
Okay. B equals what?
0, 0.
0, 0. Next row,
1 over
1
M1.
over M1, 0. Next row, 0, 0. Next row, 0, 1 over M2. C equals 1, 0, 0, 0. Next row, 0, 0, 1, 0. That's it. D equals 0, 0, 0, 0. I could have also done zeros 2 by 2. That would have done the same thing. All right. Let's say we are going to simulate, let's say we want G equal to our state space A, B, C, D. And let's just simulate some initial conditions here. I'll say initial, we're going to simulate G, and I'm going to give it some initial conditions. So I need to define initial conditions for our state vector. So our state will be, let's say 0 is S1. We'll say S1 dot is also 0. Let's just pull S2 to the right by 1. And we'll say S2 dot is 0. So all I'm saying is I'm going to take this system, I'm going to pull S2 to the right. We're going to start at rest with it stretched to the right, and I'm going to let it go. And we're going to see what happens.
Wait, what? It's not stretched. Am I saying 1? You say it's stretched.
What?
Okay, no, I'm sorry.
Boing, 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 boing. All right, I have 2 different states. State 1 is up on the top. That's S1, S2. This thing goes, whoa. You did it. You simulated a state space system. In fact, you did a non-trivial one because you did a 4 degree of freedom state space system. There were 4 values in our state vector, so it's 4 degree of freedom. Well done. You're done for today. Thank you.
Let's do it by hand.
Let's do it by hand.
Graph by hand.
I'd rather not. Did I ever have a Noah show up? Noah, no. Riley. Andrew B. Valeria. Valeria, I heard you. Tafari. Tafari, thank you. Yep. Leland, Joseph, Natalia, Dimitri, Alan, Ron. I didn't see Angela, Haley, Kamani. It was kind of what you expected. I didn't. Spencer Hawes? No. Dylan Hendry? No. Mark, I got you. Like Superman too much. Me and John Hodo. Travis Johnson, Omar Jones, Taylor, Nadal, Hannah, Alex. Did Mup ever show up? Nope. Jake Marcus. Mario? I didn't see Mario. He was here? Okay. Mark, William Neely, Angela, Melissa, Josh, Carla, pause. Yep, thank you, Carla. Melinda, Anthony Plana. You're in. I also have your homework. Hold on just a second. Amir, Jerry, Shane Rober. I didn't see Shane. Did I have Jacob Schallhorn? Yes? Okay, got it. Thanks, Jacob. Schneider, Rhonda, Alex Valdez, Luke, Martin, Ronald, Adam, Dylan Wood. Natalie Zamora. Okay. Oh, really? All right, Noah, not here. Tafari just left. Carla. Carla? Dylan. Thank you. Angel not here. Dawn not here. Shane not here. Mark Nas also left. Spencer Hawes. Anthony Plana. Anthony. Sorry. Already forgot. Dylan Hendry. Mario. Valeria. Josh. That's you.
Thank you.
Who else am I missing?
You might not have got me for attendance. Andrew B.
Andrew B. Thank you, Andrew B. Gotcha.
I had a question. Are you available for office hours either tomorrow from 4 to 5 or Thursday from 4 to 5?
Great question. Let me look. Wednesday, 4 to 5. Unfortunately, no. And then the other one is Thursday?
Yeah, Thursday.
I am actually.
Okay.
Let me add it just to be certain. 4 to 5. But I'll have to leave right at 5.
Yeah.
Got it.
Were you thank you so much.
Absolutely.
earlier?
I got you, Josh.
Okay, thank you.
Yep. Hi, question?
Hi. No, I just wanted to more formally introduce myself. I'm on your senior design
Oh,
team.
great.
Yeah, the scuba diving one.
So fun.
Yeah,
I'm excited.
I know, me too. Yeah, I just want to say hey.
Hey, we need to set up a meeting, don't we?
Yeah, I'm pretty sure we're meeting as a team today
Okay.
around 3. I think we'll probably send out an email and figure out what times work for us. And
Sounds
then we'll, any particular times that work for you, just thinking ahead.
Mondays and Thursdays are my most free days. Do you know how to look at somebody else's Outlook calendar?
No.
Okay, let me show you. It's magic. So if you go up here, wait, is that right? No. I'm on my Outlook calendar already. I can go add calendar and add from directory. Choose just your whatever account comes up, and you can type in my email and hit add. It'll show up here under the people's calendars, and then when you select it, it'll add my calendar to your calendar, so you can see when I'm
that's so
available.
cool.
It doesn't show. See how it just says busy?
Yeah.
It doesn't show you what I'm doing. It just
it
tells
shows
you
you
when
what-
I'm free.
Okay.
It
perfect.
saves like 8 emails.
Yeah, okay. Good to know. Thank you so much.
Yep, you're welcome. See ya.
Yeah.